Welcome to the course Stability Aspects of Structural Steel Design, Concepts and Applications. In this class, we will talk about post-critical buckling of plates. So far, we have discussed the buckling of columns as well as the buckling of beams, where P is the applied load and the lateral displacement is given in the x-axis. The lateral displacement can be U or V for columns and lateral displacement U or the rotation gamma for beams. So the point corresponding to that is known as bifurcation point, where P reaches P critical, and the line corresponding to the bifurcation point is called neutral equilibrium. Below the neutral equilibrium, we have stable equilibrium. Above that, we have unstable equilibrium. And the columns, we know that has three different types of buckling modes. It can fail in flexural buckling FB, torsional buckling TB, or flexural torsional buckling FTB. So the equation for flexural buckling is P critical is pi square EI divided by KL the whole square. For torsional buckling, P critical is P gamma, that is equal to 1 by R naught square into GJ plus pi square EI sub W divided by KL the whole square. For flexural torsional buckling, we have P critical equal to P gamma plus Px divided by 2 into 1 minus x naught square divided by R naught square into 1 minus root of 1 minus 4 Px into P gamma into 1 minus x naught square by R naught square divided by Px plus P gamma the whole square. Now, when it comes to beam, we have two different types of global buckling, which is lateral buckling LB or lateral torsional buckling, which is LTB. Now, the M naught critical is given as pi square EIY divided by L sub LT the whole square into root of IW divided by IY plus GJ into L sub LT the whole square divided by pi square EIY. Now, all these things corresponds to global buckling modes of failure. However, structural steel sections consist of plate elements such as flanges, web and stiffeners. Under compression, these elements with high slenderness ratios, that is width to thickness ratio or depth to thickness ratio, becomes unstable and can buckle locally. This phenomena is known as local buckling. Now, let's understand the difference between columns and plates. Unlike columns, plates continue to support loads even after buckling. In the case of an ideal column, as the axial load is increased, the lateral displacement remains zero until the attainment of critical buckling load, also known as Euler load. If the axial load versus lateral displacement is plotted, as you can see on the left hand side, we will get a line along the load axis up to P equal to P critical, which means that there won't be any lateral displacement until it reaches P critical, and this is called the fundamental path. And the fundamental path ends at the bifurcation point. When the axial load reaches the Euler buckling load, the lateral displacement increases indefinitely at constant load. This is the secondary path, which bifurcates from the fundamental path at the buckling load. The secondary path for columns represents the neutral equilibrium. You can see in the green color arrow mark, which is shown as the secondary path. Basically, it bifurcates at that bifurcation point, and the lateral displacement is theoretically known to be infinity, as you can see from the plot. The fundamental path for a perfectly flat plate is similar to that of an ideal column. So what you can see is that two different types of load versus lateral displacement plot. The one corresponding to the left side is basically for columns. The one corresponding to the right side figure is the plates. The fundamental path for both of them are the same. In the y-axis, we have a non-dimensionalized load ratio, which is P by P critical. And when P reaches P critical, which is P by P critical equal to 1.0, it bifurcates. And the lateral displacement is given in the x-axis for columns as well as for the plates. And you can see that once it reaches the bifurcation point, for a column, the secondary path is basically a straight line, which means that for a constant load, there is infinite amount of lateral displacement. In the right-hand side of the plot, as you can see that when P reaches P critical, that is P by P critical equal to 1.0, it continues to take load and it is also stable. So the secondary path, as you can see, that is not a flat line, but it is a nonlinear one compared to the columns. So at the critical load, the fundamental path for both columns and plates bifurcates into a secondary path as shown in the figure. However, for plates, the secondary path shows that the plates can carry loads higher than the elastic critical load. So the secondary path is shown here on the left hand side as well as the right hand side. The left hand side, as you can see, that it is a constant one, whereas in the right hand side, it continues to take load for the plates. Further, the secondary path for plates is stable. Therefore, the elastic buckling of a plate need not be considered as a collapse load. The elastic critical buckling stress serves as a benchmark for understanding the thin plate behavior. So you can see a timeline for the plate buckling. Here you can see that from the loading until it reaches sigma critical, it is called elastic buckling. Beyond sigma critical until it reaches sigma y, it is called post buckling. And beyond sigma y until it reaches sigma u, it is called inelastic buckling. Here the terms sigma critical is a function of geometry of the plate, whereas the terms sigma y and sigma u is a material property and is the yield stress as well as the ultimate stress of the plate. So you can see that in post buckling, the strength exceeding elastic critical buckling stress but less than the yield stress. Inelastic buckling means that occurs when the strength exceeds the yield strength but before reaching the ultimate strength. And the ultimate strength is the maximum load the plate can carry independent of the deformation magnitude. The note below says that sigma y and sigma u remain constant simply because, as I described previously, it is a material property. Whereas this sigma critical is a variable and it depends upon the thickness of the plate. So for a thicker plate, you have more elastic buckling because higher T, and hence there is a less post buckling because it narrows the gap between sigma critical and sigma y. Whereas for a thin plate, the thickness is very small, so you have lesser sigma critical. And from the loading point to sigma critical, you have very less elastic buckling, but the post buckling is much higher because the gap between sigma critical and sigma y is much larger. So this is the plate post buckling behavior for thick plates as well as thin plates. So the post critical buckling of thin plates can also be represented by means of Grillage model analogy. The plate represented by vertical columns buckling under load and horizontal tiles providing restraint. As you can see on the right hand side of the figure, taken from EISI 2007, it's a buckling of a plate where the vertical lines representing the columns, the horizontal lines representing the ties, basically providing lateral restraints. So the post buckling strength is basically the ties stretch as columns buckle outward, providing the restraining motion. The restraint offers additional strength after buckling. The membrane tension and shear in actual plates can also be described as the tension in the transverse ties is represented by membrane tension and shear. The plates near the edges carry more longitudinal compression, mirroring the Grillage model. Now let's understand how the stress redistribution in post buckling takes place. So the columns near the supported edges are more restrained than those at the center. This results in more longitudinal membrane compression near the edges. Now let us study the post critical buckling of axially compressed plates. So let us consider the simply supported square plate subjected to uniaxial compression force Nx as shown in the figure below. Previously, we have used small deflection theory to obtain critical buckling stress of plates. However, large deflection analysis is used in post-critical buckling analysis of plates. Hence, the deformations in the plane of the middle surface must be accounted for transverse deflection due to bending and membrane action. The transverse boundary conditions corresponding to simply supported edges are W equal to dou square W by dou x square equal to 0 at x equal to 0, a, and W equal to dou square W by dou y square equal to 0 at y equal to 0, a, and both of them are representing the lateral displacement as well as the moment acting at the edges, which are 0. The assumptions are all edges remain straight and the plate retains its rectangular outline during bending as indicated by the dashed lines in the figure. On the left hand side, you see the dashed or the dotted lines. Here, they remain straight. The shear forces Nxy vanish along the four edges of the plate, and the edges y equal to 0, a are free to move in the y direction. Now recall that in small deflection theory of plates, we have derived von Karman's equations as follows. You can see a plate and then we can take a small cube out of that, which is a stress cube. And you can see the stresses that are acting in the cube in x direction, y direction and z direction, as well as the shear stresses that are acting. And by substituting tau zx equal to tau xz equal to 0 and tau yx equal to tau zy equal to 0 and sigma z equal to 0. Basically, this is plane stress assumption. This leads to the following figure on the right hand side, and we have d into dou square w by dou x power 4 plus 2 into dou power 4 w by dou x square dou y square plus dou power 4 w by dou y power 4 is equal to nx into dou square w by dou x square plus ny into dou square w by dou y square plus 2 nxy into dou square w by dou x dou y, which is the von Karman's equation derived for small deflection analysis of plates. Here d is the flexural rigidity of the plate, which is EH cube divided by 12 into 1 minus mu square. Now this is the von-Karman's equation for small deflection theory, and the strain terms used in deriving the above equations are based on bending alone. However, in large deflection theory, we must consider the strains due to membrane action as well. This is the fundamental difference between the small deflection as well as the large deflection. In the small deflection, we consider the strains only due to bending. In large deflection, we consider the strains due to bending plus the membrane action as well. So the strain displacement relationship due to bending in the xy plane is shown here, and epsilon x is given as dou u sub b divided by dou x, and epsilon y equal to dou v sub b divided by dou y, and gamma xy is given as dou u sub b divided by dou y plus dou v sub b divided by dou x. And the additional terms of strains due to membrane action is given in the xz plane here, where AB is the length of the plate, which is considered here a small length, which is dx, and the displacement is w, which is in the z direction. And you can see the strains that are shown here. The question is, how do we find the strain produced by stretching of plate due to membrane action? Now, let us understand what we have described in the previous classes. Due to axial shortening of bending in columns, as you can see that the columns, when they are subjected to axial load, they actually go through a small displacement before it buckles. And this displacement here is described as delta sub b, and the length of the columns reduces a little bit here. And then there is the S, which is basically the total length of the column that includes the curvature. So the delta sub b is equal to S minus L, and S equal to L plus 0 to L half into dx by dz the whole square into dz. And S minus L is given as 0 to L half into dx by dz the whole square into dz. And we know that S minus L is the axial shortening, which is delta sub b. So substituting S minus L as delta sub b, we have half into 0 to L dx by dz the whole square into dz. Now the strain is basically the change in length by the original length, which is delta sub b divided by dz, which is equal to half into 0 to L dx by dz the whole square. This is analogous to the strain in the plate due to membrane action. So when we consider for columns bending in x direction, epsilon sub b is given as half into 0 to L dx by dz the whole square. Similarly, for plates bending in z direction along x-axis, epsilon x is given as half into dou w by dou x the whole square. So we have to understand that in the columns, the displacement was in the x direction and it was along the z direction. For the plates, the displacement is in the w direction, which is in the z direction, and it is along the x direction, and that is why epsilon x for the plates is half into dou w by dou x the whole square. Now when epsilon x equal to half into dou w by dou x the whole square, epsilon y is half into dou w by dou y the whole square, and gamma xy equal to dou w by dou x into dou w by dou y. Now we have the additional strain terms. So the total strain components in the plate is given as epsilon x naught equal to dou u naught by dou x plus half into dou w by dou x the whole square. So the additional strain term is given in the red color, and similarly epsilon y naught equal to dou v naught by dou y plus half into dou w by dou y the whole square, and gamma xy equal to dou u naught by dou y plus dou v naught by dou x plus dou w by dou x into dou w by dou y. Again, the red color terms are additional strain terms due to large deflection theory or the stretching of the middle surface of the plate. Now the strain displacement relationship. So we have epsilon x naught equal to dou u naught by dou x plus half into dou w by dou x the whole square, which is equation A, and epsilon y naught equal to dou v naught by dou y plus half into dou w by dou y the whole square, which is equation B, and gamma xy naught is equal to dou u naught by dou y plus dou v naught by dou x plus dou w by dou x into dou w by dou y, which is equation C. Now the stress strain relationship is given as epsilon x naught equal to 1 by E into sigma x minus mu into sigma y, and epsilon y naught equal to 1 by E into sigma y minus mu into sigma x, and gamma xy naught is equal to 2 into 1 plus mu by E into sigma xy. Now using the force and stress strain relation for the plate, the load is given as sigma into h, whereas n is the load per unit width of the plate, and it is actually a multiplication between the stress and the thickness of the plate h. So here when we substitute n equal to sigma into h, we have epsilon x naught equal to 1 by E h into nx minus mu into ny, and epsilon y naught equal to 1 by E into h into ny minus mu into nx and gamma xy naught equal to 2 into 1 plus mu divided by E into H into nxy. Now let us simplify the deformation compatibility equation using the theory of elasticity. So which is given as dou square epsilon x naught by dou y square plus dou square epsilon y naught by dou x square minus dou square xy naught by dou x dou y is equal to 0. Now we need to substitute the terms of dou square epsilon x naught with respect to dou y square and dou square epsilon y naught with respect to dou x square and dou square gamma xy naught divided by dou x dou y. So to accomplish this one, we have to differentiate equation A twice partially with respect to y. So we have dou into epsilon x naught divided by dou y equal to dou square u naught divided by dou x dou y plus half into. So we have dou w by dou x the whole square, which when we differentiate it, we have 2 into dou w by dou x into dou square w by dou x into dou y. So when we differentiate again, we have dou square epsilon x naught divided by dou y square equal to dou cube u naught divided by dou x into dou y square plus in the previous term 1 by 2 and 2 gets cancelled. So we have dou w by dou x, and then when we differentiate dou square w by dou x dou y square, we have dou cube w by dou x dou y square plus dou square w by dou x dou y into dou square w by dou x into dou y. So we have dou square epsilon x naught by dou y square equal to dou cube u naught by dou x dou y square plus dou w by dou x into dou cube w by dou x dou y square plus dou square w by dou x dou y the whole square, which becomes equation D. Now differentiating equation B twice partially with respect to x, we have dou epsilon y naught by dou x equal to dou square v naught by dou y dou x plus half into 2 into dou w by dou y into dou square w by dou y into dou x. So when we differentiate it again with respect to x, we have dou square epsilon y naught divided by dou x square equal to dou cube v naught divided by dou y dou x square plus this 1 by 2 and 2 gets cancelled. We have dou w by dou y, which is basically kept as a constant when we differentiate it with respect to x. So the second term is dou cube w divided by dou y into dou x square. And now we are keeping dou square w by dou y into dou x as constant. And so we keep that constant. The next term is dou w by dou y, which when we differentiate it, we get dou square w by dou y into dou x. So when we simplify this further, we have dou square epsilon y naught by dou x square equal to dou cube v naught divided by dou y into dou x square plus dou w by dou y into dou cube w by dou y into dou x square plus dou square w by dou x dou y the whole square, which becomes equation E. Now from C we have gamma xy naught equal to dou u naught by dou y plus dou v naught by dou x plus dou w by dou x into dou w by dou y. Now differentiating equation C partially with respect to x and with y, we have dou x y naught divided by dou x equal to dou square u naught by dou y into dou x plus dou square v naught divided by dou x square plus dou square w by dou x square into dou w by dou x plus dou w by dou x into dou square w by dou x dou y. So when we again differentiate it with respect to y this time, dou square gamma xy divided by dou x dou y equal to dou cube u naught divided by dou y square into dou x plus dou cube v naught by dou x square into dou y plus dou square w by dou x square, which is kept constant. The next term dou w by dou x is actually differentiated as dou square w by dou y square plus dou cube w by dou x square dou y into dou w by dou y plus dou w by dou x into dou cube w by dou x dou y square plus dou square w by dou x dou y into dou square w by dou x dou y. Now we can simplify this further. We have dou square gamma xy naught divided by dou x dou y equal to dou cube u naught divided by dou y square dou x plus dou cube v naught divided by dou x square dou y plus dou square w by dou x square into dou square w by dou y square plus dou cube w by dou x square dou y into dou w by dou y plus dou w by dou x into dou cube w by dou x dou y square plus dou square w by dou x dou y the whole square, which becomes equation F. Now substituting the values in the deformation compatibility equation, we have dou square epsilon x naught by dou y square plus dou square epsilon y naught by dou x square minus dou square gamma xy naught divided by dou x dou y is equal to a big term that is seen on the right hand side after substituting D, E and F. So we can cancel some of the terms and this becomes very simplified. Now we have dou square epsilon x naught divided by dou y square plus dou square epsilon y naught divided by dou x square minus dou square gamma xy naught divided by dou x dou y is equal to dou square w by dou x dou y the whole square minus dou square w by dou x square into dou square w by dou y square. This becomes equation 2 and it is called the deformation compatibility equation. Now recall the small deflection theory, which is the equilibrium of in-plane forces, as you can see here. Now let's look at the large deflection theory, which is very similar to the small deflection theory, except that there are additional terms which are represented by the color green. The additional terms that are represented in green color are due to the stretching of the middle surface of the plate. That is membrane action. Now let's take the equilibrium of the in-plane forces using the large deflection theory. So we have summation of forces along x-axis, which is sigma fx, is equal to minus nx into cos dou w by dou x, which is on the left hand side, right? Minus is because it is actually acting opposite to the conventional direction that is chosen here. And then the next term is plus nx into dou nx by dou x into dy, which is the additional term represented in green color, into cos of dou w by dou x plus dou by dou x of dou w by dou x into dx. Basically, we are actually transforming this in the x direction. So the direction that we need to consider is the black color line that is shown here. The forces are acting in the red color line, nx and nx plus dou nx by dou x into dx. So when we transform it, we are just taking the cos theta of that angle, and hence we are getting this first term here. And then similarly, we do for nyx. You can see that at the bottom nyx. So nyx plus dou nyx by dou y into dy into cos of dou w by dou x plus dou by dou y of dou w by dou x into dy. Again, we are taking with respect to the x-axis minus nyx because it is acting in the direction opposite to the direction of the axis that we have taken. So minus nyx into cos of dou w divided by dou x into dx is equal to 0. So for small lateral deflections w, we know that using small deflection theory, sin theta equal to theta and cos theta equal to 1. So we can simplify this further. When we do so, we have minus nx into dy plus nx into dy plus dou nx by dou x into dx into dy plus ny into dx plus dou nyx by dou y into dy into dx minus nyx into dx equal to 0. So this can again be simplified. We can get the value dou nx by dou x plus dou nyx by dou y is equal to 0. Similarly, we take the summation of forces of y-axis, which is sigma fy equal to 0. We get the same set of equations, except that here we are considering in the y direction. And again, the terms that are indicated in green color are the additional terms due to large deflection theory. And we can sum up these forces as well, similar to what we used previously. And using the small deflection theory, sin theta equal to theta and cos theta equal to 1, we get these following equations. And finally, we get the simplified equation, which is dou ny by dou y plus dou nyx by dou x is equal to 0. So these are the equations that is obtained by considering the equilibrium of the in-plane forces. Now let us substitute nx equal to h into dou square f by dou x square and ny equal to h into dou square f by dou x square plus nxy equal to minus h into dou square f by dou x dou y. And these are necessary conditions for forces along edges of plate to satisfy the above equilibrium functions. Here f of x comma y is the Airy stress function, or also known as the stress potential. Now the force strain relationship we have seen previously is epsilon x naught equal to 1 by eh into nx minus mu into ny, epsilon y naught equal to 1 by eh into ny minus mu into nx, and gamma xy naught equal to 2 into 1 plus mu divided by eh into nxy. Now substituting the values of nx, ny in epsilon x naught. Epsilon x naught is given as 1 by eh into nx minus mu into ny. So when we substitute nx equal to h into dou square f by dou y square, we have 1 by eh into h into dou square f by dou y square minus mu h into dou square f by dou x square. We have epsilon x naught equal to 1 by e into dou square f by dou y square minus mu into dou square f by dou x square. Similarly, substituting the values of nx and ny in epsilon y naught, we have epsilon y naught equal to 1 by eh into ny minus mu into nx. So that is equal to 1 by h into dou square f by dou x square minus mu h into dou square f by dou y square. H gets cancelled. So we have epsilon y naught equal to 1 by e into dou square f by dou x square minus mu into dou square f by dou y square. Now substituting the value of nxy in gamma xy naught, we have gamma xy naught equal to 2 into 1 plus mu divided by EH into NXY, which is equal to 2 into 1 plus mu divided by EH into minus H into dou square F by dou X dou Y, which simplifies to minus 2 into 1 plus mu by E into dou square F by dou X dou Y. Now let us simplify equation 2, deformation compatibility equation, by substituting the values of epsilon x naught, epsilon y naught and gamma x y naught. So when we do so in the deformation compatibility equation, which is dou square by dou y square into 1 by E into dou square F by dou y square minus mu into dou square F by dou x square plus dou square by dou x square into 1 by E into dou square F by dou x square minus mu into dou square F by dou y square minus dou square by dou x dou y, and substituting that we have minus 2 into 1 plus mu divided by E into dou square F by dou x dou y is equal to dou square W by dou x dou y the whole square minus dou square W by dou x square into dou square W by dou y square. Now this equation can be further simplified, as you can see here, by differentiating the terms twice. This all becomes 1 by E into dou power 4 F by dou y power 4 minus mu into dou power 4 F by dou x square dou y square plus 1 by E into dou power 4 F by dou x power 4 minus mu into dou power 4 F by dou x square dou y square minus of minus 2 into 1 plus mu divided by E into dou power 4 F by dou x square dou y square is equal to dou square W by dou x dou y the whole square minus dou square W by dou x square into dou square W by dou square. So we take 1 by E common here and we simplify this further. We get a much simplified equation, as you can see here, which is dou power 4 F by dou x power 4 plus dou power 4 F by dou y power 4 plus 2 into dou power 4 F by dou x square dou y square is equal to E into dou square W by dou x dou y the whole square minus dou square W by dou x square into dou square W by dou y square, which becomes equation 3. Now substituting the values of Nx, Ny and Nxy in the von Karman's partial differential equations based on small deflection theory, what do we get? So using the von Karman's differential equation for small deflection theory, we have d into dou power 4 w by dou x power 4 plus 2 into dou power 4 w by dou x square dou y square plus dou power 4 w by dou y power 4 is equal to nx into dou square w by dou x square plus ny into dou square w by dou y square plus 2 nxy into dou square w by dou x dou y. Now we substitute the values of nx, ny, nxy in the above equation, where nx equal to h into dou square f by dou y square, ny equal to h into dou square f by dou x square, and nxy equal to minus h into dou square f by dou x dou y. When we do so, we get this above equation here, and we can further simplify this equation, as you can see here. We get the equation dou power 4 w by dou x power 4 plus 2 into dou power 4 w by dou x square dou y square plus dou power 4 w by dou y power 4 minus h by d, which is basically bringing the right hand side of the equation to the left hand side and dividing the entire equation with d. We have minus h by d into dou square f by dou y square into dou square w by dou x square plus dou square f by dou x square into dou square w by dou y square minus 2 into dou square f by dou x dou y into dou square w by dou x dou y is equal to 0, which becomes equation 4. Eliminating the term w in equation 3. Now we have an objective to eliminate w in equation 3. We have to assume that the deflection function w is given as f into sin pi x by a into sin pi y by a. So substituting the above deflection function in equation 3 gives the following. So to do so, we have to differentiate the function w equal to f into sin pi x by a into sin pi y by a several times to substitute in the equation 3 shown below. So we have dou w by dou x equal to f into pi by a into cos pi x by a into sin pi y by a, and dou w by dou y equal to f into pi by a into sin pi x by a into cos pi y by a. So when we differentiate dou w by dou x one more time, we have dou square w by dou x square, which is equal to f into pi by a the whole square into minus sin pi x by a into sin pi y by a, and dou square w by dou y square equal to f into pi by a the whole square into sin pi x by a into minus of sin pi y by a. So now the term dou square w by dou x square into dou square w by dou y square is equal to f square into pi by a the whole power 4 into sin square pi x by a into sin square pi y by a. Basically, we are multiplying dou square w by dou x square and dou square w by dou y square, where each term contains f into pi by a the whole square. So f into f becomes f square, pi by a the whole square into pi by a the whole square becomes pi by a the whole power 4. Sin pi x by a into sin pi x by a becomes sin square pi x by a. Similarly, sin pi y by a into sin pi y by a becomes sin square pi y by a. Minus into minus becomes plus. And hence we get the term f square into pi by a the whole power 4 into sin square pi x by a into sin square pi y by a. So we can substitute these terms to the left hand side as shown here. And to simplify this further, we need to employ our high school mathematics, which is cos 2 theta equal to 2 cos square theta minus 1. And cos 2 theta can also be written as 1 minus 2 sin square theta. So when we plug it back, we have cos square theta equal to 1 by 2 into 1 plus cos 2 theta. Here we are representing in terms of alpha. So cos square alpha equal to 1 by 2 into 1 plus cos 2 alpha. And sin square alpha equal to 1 by 2 into 1 minus cos 2 alpha. So when we substitute the terms to the left hand side of the equation and we simplify this further, we get the equations that are seen in the screen. And we can simplify this further. Basically, basic algebraic equation. We are taking f square into pi by a the whole power 4 outside. So it becomes e into f square into pi by a the whole power 4. And 1 by 2 into 1 by 2 becomes 1 by 4. So we have e f square pi by a the whole power 4 divided by 4 into 1 plus cos 2 pi x by a plus cos 2 pi y by a plus cos 2 pi x by a into cos 2 pi y by a minus the other term, which is 1 minus cos 2 pi x by a minus cos 2 pi y by a plus cos 2 pi x by a into cos 2 pi y by a. When we simplify these terms, most of the terms get cancelled. So 1 and minus 1 get cancelled. And the cos 2 pi x by a into cos 2 pi y by a terms also gets cancelled. So we have a simplified equation now becoming e into f square into pi by a the whole power 4 divided by 4 into 2 cos 2 pi x by a plus 2 cos 2 pi y by a. So this is written as shown below. This becomes equation 5. Now let us find the solution of the partial differential equation. Here f is given as fc plus fp. So for complementary solution, we assume the term f sub c equal to a into y square. Now why did we choose the term? To obtain the complementary solution of equation 5, one sets the right hand side of the equation is equal to 0. Thus, the complementary solution of equation 5 corresponds to the in-plane stress distribution that exists in the plate just prior to buckling. So, at the instant, the in-plane stresses are known to consist of a uniform stress due to nx, y, ny and nxy is equal to 0. Now, we know that nx equal to h into dou square f by dou y square. So, nx not equal to 0, which means that h into dou square f by dou y square is not equal to 0. So, the f sub c should be a function of y. So, now finding the value of a, we have fc equal to a into y square. So, dou f by dou y equal to 2ay and dou square f by dou y square equal to 2a. We also know that nx equal to minus sigma xa into h, which is the basic understanding of the critical buckling load nx, which is the stress multiplied by the thickness, because nx represents the load per unit width of the plate and minus is due to the compressive forces that are acting. So we have h into dou square f by dou y square equal to minus sigma xa into h. So we have dou square f by dou y square equal to minus sigma xa. So comparing it with dou square f by dou y square equal to 2a, we have a equal to minus sigma xa by 2. And then dou square f by dou y square equal to 2 into minus sigma xa by 2, which becomes equation 6. Now, substituting the value of a in f sub c, we get f sub c equal to minus sigma xa into y square by 2. This is for the complementary solution. Now, let's look at the particular solution. From equation 5, we have dou power 4 f by dou x power 4 plus 2 into dou power 4 f by dou x square dou y square plus dou power 4 f by dou y power 4 is equal to f square into e into pi power 4 divided by 2a power 4 into cos 2 pi x by a plus cos 2 pi y by a. Since the non-homogeneous part, which is the right hand side of partial differential equation, has trigonometric terms, the particular solution is assumed as follows, which is f sub p equal to b into cos 2 pi x by a plus c into cos 2 pi y by a. Finding the value of b and c, substituting the particular solution into equation 5 and equating the coefficients, we have dou power 4 f sub p divided by dou x power 4 plus 2 into dou power 4 f sub p divided by dou x square dou y square plus dou power 4 f sub p divided by dou y power 4 is equal to f square into e into pi power 4 divided by 2a power 4 into cos 2 pi x by a plus cos 2 pi y by a. We know that fp equal to b into cos 2 pi x by a plus c into cos 2 pi y by a. So dou fp divided by dou x equal to b into minus 2 pi by a into sin 2 pi x by a, and dou square fp by dou x square equal to b into minus into 2 pi by a the whole square into cos 2 pi x by a. And dou cube f sub p divided by dou x cube equal to b into minus into 2 pi by a the whole cube into minus sin into 2 pi x by a. And dou power 4 fp divided by dou x power 4 is equal to b into 2 pi by a the whole power 4 into cos of 2 pi x by a. Now similarly for the right hand side, which is dou fp divided by dou y equal to c into minus 2 pi by a into sin 2 pi y by a. Similarly, dou square fp divided by dou y square equal to c into minus of 2 pi by a the whole square into cos 2 pi y by a. And dou cube fp divided by dou y cube equal to c into minus 2 pi by a the whole cube into minus sin of 2 pi y by a. And dou power 4 fp by dou y power 4 is equal to c into 2 pi by a the whole power 4 into cos 2 pi y by a. And we also have dou power 4 fp by dou x square dou y square equal to dou square by dou y square into b into minus of 2 pi by a the whole square into cos 2 pi x by a, which when we differentiate it, we get the value of 0 because this term does not contain any y term. So partially differentiating the terms inside the square bracket with respect to y leads to the term 0. Now when we substitute all the values that we have got in the left hand side, we have the equation here, which is b into 2 pi by a the whole power 4 into cos 2 pi x by a plus 0 plus c into 2 pi by a the whole power 4 into cos 2 pi y by a is equal to f square into e into pi power 4 divided by 2a power 4 into cos 2 pi x by a plus cos 2 pi y by a. So we can simplify this further and we get the equation which is b into cos 2 pi x by a plus c into cos 2 pi y by a is equal to f square into a power 4 divided by 16 pi power 4 into e into pi power 4 divided by 2a power 4 into cos 2 pi x by a plus cos 2 pi y by a. This can again be simplified, and when we do the simplification and when we equate the terms corresponding to cos 2 pi x by a, we get the value of b, and when we equate the terms corresponding to cos 2 pi y by a, we get the values of c. So when we do so, we have b equal to c equal to e into f square divided by 32. Now that's the particular solution. Fp equal to b into cos into 2 pi x by a plus c into cos into 2 pi y by a. Substituting the terms b equal to c equal to e f square by 32 in f sub p, we have fp equal to e f square by 32 into cos 2 pi x by a plus cos 2 pi y by a. The total solution is the summation of complementary solution plus the particular solution, which is f equal to e into f square by 32 into cos 2 pi x by a plus cos 2 pi y by a minus sigma xa into y square by 2. This becomes equation 7. So far, 2 steps in the analysis have been completed. We have eliminated the term w in equation 3 by assuming an approximation for w and obtained a solution for Airy stress function f. There remains one final calculation of the coefficient f in accordance with equation 4. From equation 4, we have dou power 4 w by dou x power 4 plus 2 into dou power 4 w by dou x square dou y square plus dou power 4 w by dou y power 4 minus h by t into dou square f by dou y square into dou square w by dou x square plus dou square f by dou x square into dou square w by dou y square minus 2 into dou square f by dou x dou y into dou square w by dou x dou y is equal to 0. Now, unlike equation 5, the non-homogeneous part of equation 4 is coupled with f and w terms. Hence, it is difficult to obtain a direct solution for equation 4. Therefore, we shall use f from equation 7 and adopt Galerkin method, which is an approximate method to solve differential equations to obtain the solution for equation 4. The Galerkin form of the above equation is double integral of 0 to a into q of f into g of x comma y into dx into dy is equal to 0. Now, q of f is the left hand side of equation 4 and g of x comma y is the variable part of w. Substituting the values of w and f, we have q of f equal to dou power 4 w by dou x power 4 plus 2 into dou power 4 w by dou x square dou y square plus dou power 4 w by dou x power 4 minus h by t into dou square f by dou y square into dou square w by dou x square plus dou square f by dou x square into dou square w by dou y square minus 2 into dou square f by dou x dou y into dou square w by dou x dou y. And g of x comma y equal to sine of pi x by a into sine of pi y by a. Now let us substitute the derivatives in q of f. We get the equations to be substituted on the right hand side, which is basically the derivatives to be used in the problem. So these are all simple partial derivatives. We have f equal to e into f square by 32 into cos 2 pi x by a plus cos 2 pi y by a minus sigma xa into y square by 2. So when we differentiate it with respect to x, dou f by dou x equal to e f square by 32 into 2 pi by a into cos becomes sine, so minus sine into 2 pi x by a, and the rest of the terms become 0. And we have dou square f by dou x into dou y. Basically, we differentiate the same equation with respect to y. The terms are all with respect to x, so dou square f by dou x dou y becomes 0. Now we differentiate dou f by dou x one more time. We have dou square f by dou x square, which is equal to e f square by 32 into 2 pi by a the whole square, because when we differentiate the sine term, we have this 2 pi by a which gets multiplied with the previous 2 pi by a, so it becomes 2 pi by a the whole square. And the minus term remains the same. Sine becomes cos, so it becomes minus cos 2 pi x by a. And similarly, when we differentiate it with respect to y, we have dou square f by dou y square equal to e f square by 32 into 2 pi by a the whole square into minus cos 2 pi y by a into minus sigma xa. The minus sigma xa term is to be understood because y square by 2, when we differentiate it once, it becomes 2y by 2, basically y, and we differentiate it one more time, y becomes 1. So the term minus sigma xa remains same. So that is why we get dou square f by dou y square equal to e into f square by 32 into 2 pi by a the whole square into minus cos 2 pi y by a minus of sigma xa. And we have the diffraction function. W is described as f into sin pi x by a into sin pi y by a. We have already did this derivation, which is dou w by dou x equal to f pi by a into cos pi x by a into sin pi y by a. Dou square w by dou x square equal to minus f into pi square by a square into sin pi x by a into sin pi y by a. And then we differentiate it one more time now with respect to y, which is dou cube w by dou x square into dou y equal to minus f into pi cube by a cube into sin pi x by a into cos pi y by a. And we have dou cube w by dou x cube. Basically, we differentiate dou square w by dou x square. So dou cube w by dou x cube equal to minus f into pi cube by a cube into cos pi x by a into sin pi y by a. Now we differentiate that one more time. We have dou power 4 w by dou x power 4 equal to f into pi power 4 by a power 4 into sin pi x by a into sin pi y by a. Here the negative term gets cancelled because when we differentiate cos, we have minus sign, and already there is a minus there. So minus into minus becomes plus. So we have dou power 4 w by dou x power 4 equal to f into pi power 4 by a power 4 into sin pi x by a into sin pi y by a. And we have dou power 4 w by dou y power 4 is equal to f into pi power 4 by a power 4 into sin pi x by a into sin pi y by a. Now we need to have the term dou power 4 w by dou x square dou y square. So we take dou cube w by dou x square into dou y. So we differentiate that one more time with respect to y. We have f into pi power 4 divided by a power 4 into sin pi x by a into sin pi y by a. The negative term gets cancelled because when we differentiate cos, we get minus sign. So there is already a minus sign there. So we have minus into minus plus. So dou power 4 w by dou x square dou y square equal to f into pi power 4 by a power 4 into sin pi x by a into sin pi y by a. Now we substitute that in the left hand side of the equation. We get a mega equation as you can see in the screen. Right? We can simplify this equation. We can take 1 by d common here for the entire equation, and then applying simple algebra, and we get the equation as you can see in the screen. We can simplify this further as you can see on the picture, and we can simplify this further. Okay, no big deal here, basic algebra here. And then when we do so, we have q of f equal to 1 by d into 4f into d into pi power 4 by a power 4 minus e h into f cube into pi power 4 by 8 a power 4 into cos 2 pi x by a plus cos 2 pi y by a minus sigma x a into h into f into pi square by a square into sin pi x by a into sin pi y by a, which is basically the common term which we have taken out. Now we also know that g of x comma y equal to sin pi x by a into sin pi y by a. So substituting q of f and g of x comma y in the Galerkin equation, which is double integral of 0 to a q of f into g of x comma y into dx into dy is equal to 0. We put this equation here, we get a bigger equation again, as you can see in the screen. And this again we are multiplying with the terms given for g of x comma y, which is sin pi x by a into sin pi y by a. So now we use the identities and the integrals to be used in the problem, which is cos 2 pi x by a into sin square pi x by a is equal to half into cos 2 pi x by a minus cos square 2 pi x by a, and integral of 0 to a sin square pi x by a into dx equal to a by 2, integral of 0 to a cos 2 pi x by a into dx equal to 0, and integral of 0 to a sin square pi y by a into dy equal to a by 2. We substitute that in the above equation and we can simplify this further, as you can see here. And the final simplified equation is given here, which is sigma xa equal to 4 into d into pi power 4 divided by h into a square plus e pi square into f square by 8a square. Now we know that sigma critical equal to 4d into pi power 4 by h into a square for a simply supported plate with uniaxial uniform compression. So we have sigma xa equal to sigma critical plus e into pi square into f square by 8a square, where xa equal to average value of the applied compressive stress. Now let's look at the post-critical buckling of axially compressed plates. We can see that the load displacement plot here, which is the plot with respect to sigma critical in the y-axis and f in the x-axis. When we do so, we see that the sigma xa equal to sigma critical, which is the base value, plus due to the post-critical buckling, we have additional strength, which is E into pi square into f square divided by 8a square. Here the equation gives the relationship between the average applied compressive stress sigma xa and the maximum lateral deflection F, which is subsequent to the onset of buckling. Now the plate begins to deflect laterally at the critical load predicted by the linear theory. Beyond that point, as long as the lateral deflection is infinitely small, the stiffness of the plate is 0. That is, the load deflection curve has a 0 slope. However, as soon as the lateral deflection becomes finite, as you can see on the left hand side of the plate, the stiffness starts to increase and continues to do so as the deflection grows. It is possible for the plate to resist axial loads in excess of the critical load subsequent to buckling. This characteristic of the plate, known as post-buckling strength, is of extreme importance in thin wall structures. Because of it, thin plates, even though they may buckle at very small stresses, are able to resist sizable loads without collapsing. Now let us look at the non-uniform stress distribution due to post-critical buckling of thin plates. To understand post-buckling strength of thin plates, it is necessary to consider the middle surface stresses that exist subsequent to buckling. So the longitudinal stress along x direction, which is sigma x, we know that nx equal to h into dou square f by dou y square, and substituting nx equal to minus sigma x into h, we have minus sigma x into h equal to h into dou square f by dou y square. So we have sigma x equal to minus dou square f by dou y square. We also know that f equal to e into f square divided by 32 into cos 2 pi x by a plus cos 2 pi y by a minus sigma xa into y square by 2. This we have derived in the previous slides. So when we substitute that here in the sigma x equation, which is sigma x equal to minus of dou square f by dou y square, when we simplify this further, we have sigma x equal to e into pi square into f square divided by 8a square into cos 2 pi y by a plus sigma xa. Now let's look at the transverse stress along y direction, sigma y. We know that ny equal to h into dou square f by dou x square. Substituting ny equal to minus sigma y into h, we have minus sigma y into h equal to h into dou square f by dou y square. So we have sigma y equal to minus dou square f by dou y square. Taking f equal to e into f square by 32 into cos 2 pi x by a plus cos 2 pi y by a minus sigma xa into y square by 2. We have dou square by dou x square into e into f square by 32 into cos 2 pi x by a plus cos 2 pi y by a minus sigma xa into y square by 2. So when we do so, we get a simplified equation, as you can see here, which is sigma y equal to e into f square into pi square divided by 8a square into cos 2 pi x by a. Now we got the equation for sigma x and we got the equation for sigma y. Sigma x is the longitudinal stress along x direction and sigma y is the transverse stress along the y direction. We also know that sigma xa equal to sigma critical plus E into pi square into f square by 8a square. So we can derive f square equal to 8a square divided by E into pi square into sigma xa minus sigma critical. Now substituting the value of f square into the above equations, we have longitudinal stress along the x direction sigma x is equal to E into pi square divided by 8a square into 8a square divided by E pi square into sigma xa minus sigma critical into cos 2 pi y by a plus sigma xa. So we can cancel the terms 8a square and E pi square and E pi square. So we have sigma xa equal to sigma xa minus sigma critical into cos 2 pi y by a plus sigma xa. And similarly, the transverse stress along the y direction sigma y is given as sigma y equal to E into pi square divided by 8a square into E pi square into sigma xa minus sigma critical into cos 2 pi x by a. So similarly, we get sigma y equal to sigma xa minus sigma critical into cos 2 pi x by a, which when we plot, we get the stress distribution as you can see on the right hand side after the elastic critical buckling stress. You can see a nonlinear stress distribution that takes place along the longitudinal edges as well as in the transverse direction as you can see here. Now, here we have the average applied stress sigma xa equal to sigma critical plus E pi square into f square by 8a square, which is indicating that the sigma xa is the elastic critical buckling stress plus the green color terms, which is the additional strength due to post buckling. Let us understand the non-uniform stress distribution due to post-critical buckling of thin plates with an example. Assume an average applied stress of sigma xa equal to 500 MPa. As you can see here on the right hand side, a stress of 500 MPa is applied and all four sides are simply supported. The SS represents a simply supported condition. Now, let us find the contribution towards critical stress and the non-uniformity of stress due to post-critical buckling. We know that sigma xa equal to sigma critical plus E into pi square into f square by 8a square. So now let us find out sigma critical, which is given as k into pi square E divided by 12 into 1 minus mu square into b by t the whole square. Here, since it is all four sides simply supported, let us take k equal to 4. So 4 pi square into 2 into 10 power 5 divided by 12 into 1 minus mu square, which is 12 into 1 minus 0.3 the whole square into b by t, which is 100 by 2. So the width of the plate is 100 and the thickness of the plate is 2. So when we do so, we have sigma critical equal to 451.9 MPa. Now we know that E pi square f square by 8a square equal to sigma xa minus sigma critical. So we have sigma xa is the applied stress, which is 500 and sigma critical is 451.9. So this value is 48.1 MPa. Now let us substitute these values in sigma x and sigma y to obtain the non-uniform stress distribution. So we have sigma xa equal to 500 MPa equal to 451.9 MPa plus 48.1 MPa. And we have this post-buckling stress that can be determined at various locations. We split the width and the length of the plate as 4 divisions, which is 0, a by 4, a by 2 and 3a by 4 and a. So due to post-buckling, we know that the longitudinal stress along x direction sigma x is given as sigma x equal to E into pi square into f square by 8a square into cos 2 pi y by a plus sigma xa. So which is nothing but 48.1, which we have actually calculated in the previous slide, which is 48.1 into cos 2 pi y by a plus sigma xa. And the transverse stress along y direction sigma y is given as E pi square f square by 8a square into cos 2 pi x by a. This is equal to 48.1 into cos 2 pi x by a. So at y equal to 0, what happens? At y equal to 0, 48.1 into cos of 2 pi 0 by a, cos 0 is 1, so we get the value of 48.1. Now at y equal to a by 4, we have 48.1 into cos of 2 pi into a by 4 by a, which becomes cos pi by 2, cos pi by 2 equal to 0, so the entire term becomes 0. Now let's look at y equal to a by 2. So we have 48.1 into cos into 2 pi into a by 2 by a. We have cos pi, which is minus 1. So we have minus 48.1. Now the next term is y equal to 3a by 4, which is 48.1 into cos into 2 pi into 3a by 4 by a. which again is a multiple of pi by 2, and so it becomes 0. Now we have at y equal to a 48.1 into cos of 2 pi a by a. We have cos 2 pi is 1, so we have 48.1. Similarly, at x equal to 0, we have 48.1 into cos 2 pi into 0 by a, which is 48.1. At a by 4, we have 48.1 into cos of pi by 2, which is 0. At a by 2, we have 48.1 into cos of pi, which is minus 1. So, we have minus 48.1. At x equal to 3a by 4, we have 48.1 into cos of 2 pi into 3a by 4 by a, which is a multiple of pi by 2, which is equal to 0. And at x equal to a, we have 48.1 into cos 2 pi into a by a, cos 2 pi equal to 1, we have 48.1. So, this is the effect of the non-uniform stress distribution as a result of post-critical buckling of thin plates, which when plotted, you can see that there is a 48.1 that is acting at the edges of the plate here, and then it goes to 0, and then it goes to negative 48.1, and then it goes to 0, and then we have positive 48.1, which is compressive in nature, which is in the x direction. Now, when we plot the same in the y direction, we have 48.1, and then we have at the beginning we have 48.1, and then it goes to 0, and then we have negative 48.1, and then it again goes to 0, and then we have 48.1. Now, the total stress distribution should be taken into consideration. So, this is the stress due to elastic buckling, and then this is the stress due to post buckling, which is non-linear in nature. When we add the two, we get the stresses due to elastic buckling plus the stresses due to post buckling, right? So, when we add, we have this stress distribution here. Basically, we have 500 plus 48.1, which becomes 548.1 at the edges. At the center, we have 500 minus 48.1, which turns into 451.9 at the center. This is in the x direction and the loaded direction. Basically, there is a nonlinear stress distribution that takes place due to post buckling. And then at the y direction, which is transverse in nature, we have 48.1, which is basically compressive in nature. And then there is a tensile pulling that takes place, which is again minus 48.1, which is tensile in nature. And then we have 48.1, which is basically compressive. So, what we can see here is that this 48.1 is an additional term that we can see, which is tensile in nature, which actually is extending or stretching the plate and making it carry more load. And this is the beauty of post-buckling reserve capacity. So, there are transverse stresses sigma y present subsequent to buckling, where none existed prior to buckling, and the longitudinal stress sigma x, which was constant up to the onset of buckling, varies across the width of the plate after buckling has begun. The transverse stresses that are present in the post-buckling range vary from a maximum compressive stress at the edges x equal to 0, a to a maximum tensile stress at the center of the plate. Of these, the tension stresses is the most important, as we can see, that is represented in the green color. Its presence tends to stiffen the plate against the lateral deflection and to prevent collapse from occurring after the critical load has been reached. The post-buckling strength exhibited by the plate can be attributed to the middle surface tensile stresses sigma y that arises subsequent to the onset of buckling. Now, when we plot it, we have sigma xa equal to sigma critical plus E into pi square into f square by 8a square. As you can see, the critical buckling stress of the plate, which is represented in the y direction, and the large displacement, which is represented in the x direction in terms of f. So, we can see the stress distribution, which is non-linear in nature after the critical buckling has been attained and post-buckling has been initiated. So, the main conclusions are plates can continue to carry load subsequent to reaching the critical stress by virtue of post-buckling strength. Transverse tensile stresses that arise subsequent to the start of buckling are primarily responsible for the presence of post-buckling strength in plates. The material near the longitudinal edges of the plate resists most of the increase in the load that occurs in the post-buckling range. Thank you very much, and we look forward to meeting you in the next class.